Hey everyone, I had a request to go over the Chapter 16 homework. I'm sorry this is a little late. I'm still getting it out on a Saturday as promised. I know it's a little later in the day, but I've been grading your exams, as hopefully you all know, so I do apologize for the late video, but at least it's only 3 questions, so we are going to go ahead and go through them. If I could grab my binder, not with my work in it, not that I didn't put right next to me. Okay, so number 1, we are told to compute the change in Gibbs free energy for a reaction of 1.3 kilograms of ocean water as liquid water with the atmosphere, nitrogen and oxygen, to form aqueous nitric acid. And we're told H plus and NO3 minus under standard thermodynamic conditions at 298.15 Kelvin. The standard Gibbs free energy formation for nitrate ion in aqueous solution is negative 111.3 kilojoules per mole. And this is an important number, as you will need this. Okay, so the first thing we need to do is write our reaction. So we're told it's water, which is a liquid, and nitrogen and oxygen gas, and these are reacting to form H plus and NO3 minus. So we need to balance this equation. I'm just going to go ahead and balance it and show you 2, 2, and then we can put a 2.5 in front of oxygen to make our lives easier. And there we are, balanced. Just gotta put gas and gas. Okay, so the next thing we need to do is go to our appendix in the book. So we go to Appendix G, and we need to go ahead and get the delta G standards of formation for everything here, except we were already given it for nitrate. Oops, let me fix these. These are not gaseous, these are aqueous. Sorry. Okay, so looking at our reactants, the delta G standard of formation for water, for liquid water, is equal to negative 237.1 kilojoules per mole. For nitrogen, it's 0. And for oxygen, it is also 0. And then we need to look it up for H plus. So the delta G standard of formation for H plus is equal to 0. And then they gave us delta G formation for nitrate. Negative 108.7 kilojoules per mole. So one thing that we learned about delta G is it's very similar to delta H in that you do the products minus reactants, you do the sums, and that gets you your delta G for the reaction. So delta G, So delta G of formation for our reaction is going to equal the products, and we have to do each of the delta G's of each product times the number of moles from the balanced reaction. So we have 2 hydrogens times 0 plus 2 nitrates times negative 108.7. And these are our products minus our reactants. We have 1 water at negative 237.1 plus 1 nitrogen at 0 and plus 2.5 oxygens that are also 0. So then this gets us negative 222.6 minus negative 237.1, makes that positive. So this gets us positive 14.5 kilojoules per mole. So that's our first step here. And we want just kilojoules. We don't want per mole because we are looking at an amount, 1.3 kilograms of water. So we need to take this 1.3 kilograms and turn it into moles because our units for delta G are kilojoules per mole. So we need moles of water. So we start with 1.3 kilograms of water. And then we'll start by putting this into grams. We have 1,000 grams of water for every 1 kilogram. And then we can go ahead and change this to moles using molar mass. So we have 1 mole of water for every 18.02 grams of water. Grams cancel. Now we have moles, and then we can go ahead and use this delta G formation as a conversion factor to go from moles to kilojoules. So we have 14.5 kilojoules for every 1 mole. And so then that cancels out our moles, and we are left with 1,046 kilojoules. I think the trickiest part here was realizing that they gave you the Gibbs free energy of formation for nitrate ion, because if you look in the back of your book, there actually is a value for nitrate, but it's not aqueous nitrate. So that's your big thing there, is that the aqueous nitrate has a bit of a different delta G. So in the book, it says like it's negative 108 or so, and that actually throws your answer off quite a bit. Even though it's only a couple kilojoules, it does make a big difference. Number 2, we want to calculate the standard change in Gibbs free energy for the reaction 2NO2 going to N2O4 at 56 degrees Celsius. And then they give us a table with delta H and S. So we know that delta G is equal to delta H minus T delta S. So let's go ahead and calculate our different parts. So delta H is equal to products minus reactants. And we have 1 mole of N2O4 times its delta H, which is 11.1. And remember, these are kilojoules per mole. Whoops. Minus 2, because we have 2 NOs, times 33.2. And that gives us negative 55.3 kilojoules per mole. And I just went and turned this into joules. You can leave it as kilojoules and then change the entropy into joules. It's really, into kilojoules. It's really up to you. Doesn't really matter. Okay, and now delta S. Same type of thing. We have 1 times N2O4, which is 304.4, minus 2 times 240.1. And this gives us negative 175.8, and these are joules per mole Kelvin. And then if we go ahead and multiply this times the temperature, which we were told 56 degrees Celsius, we have to add 273 to that to make it Kelvin, so this is 329 Kelvin. So multiply this times 329 Kelvin, Kelvins cancel, and so then that tells us that T times delta S is equal to negative 57,838 joules per mole. So then delta G is equal to negative 55,300. That's delta H minus negative 57,800. Just rewrite that so it looks prettier. 838. And so this gives us 2,538 joules per mole. And the answer they want in kilojoules per mole, so this is 2.538 kilojoules per mole. So this was a nice delta G equals delta H minus T delta S problem. So number 3 ended up being really challenging, and I'm sorry, when I first read it, I didn't realize exactly what it entailed. So I'm gonna just kind of give you the numbers that'll solve it for you. I will not give you something like this on your exam. Again, I apologize for this one. I'm just even gonna write it here for the people that don't bother watching or listening to the videos. Oops, sorry for this. So you can look up delta H reaction for this. The balanced reaction ends up being 2CO plus O2 is 2CO2. So a couple things that we need to find: the moles of CO. And so that's equal to 3.3 grams of it. So you might have a different grams, but same type of thing, times 1 mole of CO per 28.01 grams. So there's 0.117815 moles of CO. So then delta S, standard for this reaction, actually I'm going to write these at the top so there's more room. You can look up these values, and I'm just going to give them to you, and then that'll basically be the biggest bit of information you need. Delta H for the reaction is negative 283.0 kilojoules per mole. And delta S for the reaction is equal to negative 86.5 joules per mole Kelvin. You can always go and calculate this since you have the balanced reaction. You can go and do that perfectly fine. But I'm just giving these to you to hopefully make your lives a little easier. So we also know that the delta S of the universe is equal to delta S of the system plus delta S of your surroundings. So let's go ahead and find delta S for our system. So that is going to equal our moles. We have this 0.117815 moles that are reacting, and then we have the delta S for the reaction. So times negative 86.5 joules for every 1 mole Kelvin. Moles cancel. And so then that gives us negative 10.19 joules per Kelvin. And then we can do delta S for our surroundings. And from your book, one thing it told us was that surroundings is equal to negative Q reversible over T surroundings. So in this case, it's going to be equal to negative delta H system divided by the temperature of the surroundings. So then this gives us negative times negative 283.0 kilojoules per mole divided by our temperature of 298 Kelvin. So this gives us 0.9497 kilojoules for every 1 mole Kelvin. And then we're going to multiply this, let's see, where was I? Times 1,000 joules per 1 kilojoule. And then we're also going to multiply it times our number of moles. So we get rid of the mole unit, the 0.117815 moles. Moles cancel, kilojoules are gone, so that'll give us joules per Kelvin. And so this is 111.89 joules per Kelvin. So then our delta S universe is equal to negative 10.19 joules per Kelvin plus 111.89 joules per Kelvin, and that gives a total of 101.7 joules per Kelvin. Again, I'm sorry about this one. There's a lot of steps here, as you would have to go and find delta H reaction, delta S reaction, and it's kind of a pain in the butt. And you had to be able to make that change for the delta S surroundings to be negative delta H over T. So I apologize, this was a mean problem, but hopefully this gets you through it now. All right, I hope you guys are doing well and staying safe, and have a great rest of your weekend.